Now this kind of problem is where we would start. So we can go do some other ones. I wouldn't say they're more difficult, they're just a little different. So I'm going to erase this one. Let's see. Now I'll leave it up and I'll put one over here. In fact, before we do it, let's take your observation there, buddy. And I'll give you these. These are a couple laws. So the one you mentioned is called Kirchhoff's current law. Frequently just KCL because people don't like trying to remember how to spell his name. It is right. What it says is all the current into a node equals all the current out of the node. You'll see it written as an equation at sometimes where that's summation of all the current in equals all the current out. Also is called the conservation of current. Really, these are all just different ways of stating the same thing. Currents flowing charges. If I have a node, this is a node where they all come together. This entire thing here is really the node. It's not being in a spot. It's just where they all come together. All the current that would flow in equals all the current that would flow out. I could take the node on the other end. All the current in equals the current out. Now I've also got another one. It's called Kirchhoff's voltage law, which is KVL. And it's what we've used in series circuits already. I don't think we've named it. We may have named it last semester at some point. Sum of all voltages in a loop is 0. This will frequently get stated as the summation of all the voltage drops is 0. Okay, what does that mean? Well, like I said, we've already done it. If I've got a battery and I have these voltages, I have voltage of the battery, I have the voltage drop across resistor 1, voltage drop across resistor 2, and a voltage drop across resistor 3 as we go around this direction of current. So if I were to add all those up, I would have the battery voltage would be a positive number. Voltage 1 would be a negative number because I'm dropping. Voltage 2 would be a negative number, I'm dropping. Voltage 3 is a negative number, so I'll add it to 0. We already do it. We don't think about negative numbers, and all what we do is we just say this voltage that goes in, if I sum those other three, they'll be equal to it. That is a statement of the voltage law. Now, there are times we have to really pay attention to the polarity of everything. If we have two batteries or more batteries in a circuit, we'll come back and do that later though. But yeah, since you mentioned two laws, so after Ohm's law and my series and parallel resistors, well, actually probably before my series and parallel resistors, these are the next two most critical laws for solving all circuits out there. We'll be using them over and over and over this semester. And like I said, we've already introduced them pretty much. We just didn't call them that. All right. Can I erase this board now? is also recorded, so. Let's do another one. Oh, I don't need to erase the entire table, really. I'll just erase the answers and keep my table. So we want another series parallel circuit to solve. So let's do this one. Take an 18-volt battery. Voltage R1. We'll make that a 5.6 kilo ohm. And I don't want that big one. I'm gonna change it. Sorry, you're right. 2.2 kilo. R2 is 1.2 kilo ohms. R3 is 560 ohms. Notice I'm doing two things, series parallel, and I'm making you mix and match resistors in ohms and resistors in kilo ohms, because you have to be able to do that. So let's do it. Okay, what's in series and what's in parallel, and where do I want to start? Anything you would like to answer before I start?
2.2 kilograms is like pounds easy to do, isn't it? That's just series.
Not series, parallel. The two ends are connected to the two ends of this. So this will have 18 volts across it.
Yeah.
And then I would find the current. So this is in parallel to the battery. This combination, these two are in series with each other, but the combination from here to here would be the same voltage as the battery. So again, the easiest place to start is probably to go furthest from the battery and work that. So if I look, R23 is the series combination of R2 and R3. Which is 1.2 kilo ohms, 560 ohms. So to add those, I need to convert my 1.2 kilo ohms to ohms, or convert my 560 to kilo ohms. Doesn't matter. Which do you prefer? Do you like kilo ohms better or ohms?
Kilo ohms.
Okay.
Right.
So if I add those, 1.676 kilo ohms, right? 1.2 plus 0.56. So I'm going to redraw my circuit then. I have 18 volts. I have R1, which we said is 2.2 kilo ohms. I have these two combined in series, which is my R23, which is 1.76 kilo ohms. And now they're both in parallel. I can go ahead, I'm going to go ahead and do it now. You can actually stop here. Everything's got 18 volts. You can go find their currents. Actually, let's go ahead and just do it that way. Are we okay with that? Better series down in parallel. So I look here. If I want to solve I1, I want to solve I23. I1 is the voltage across R1 divided by R1. So 18 volts over 2.2 kilo ohms. What is that? 8.1818. 8.18 milliamps. I23 is my 18 volts, because it's all in parallel, over 1.76 kiloohms. $10.23 milliamps. So I can take those and go back to my original equation. My current through R1 is 8.18 milliamps. Now, when you're comfortable with it, you don't even have to do that part to go, hey, I know this is going to be 18 volts. I can solve current Ohm's law. Over here, you can look without doing all that. Once you get comfortable, hey, these two are in series, find the series combination, find the current. Because they're going to have one current that's going to go through both of them, which is 10.23 milliamps. I'm going to come on my table and write down everything I can. 18 volts. 18 volts. 8.18 milliamps. 10.23 milliamps. Let's find these voltages. So V2 is my current, 10.23 milliamps, times my resistance, 1.2 kiloohms. .28 volts. B3. $10.23 milliamps times 560 ohms. So I need to convert my milliamps to amps as I'm going, or my ohms to kiloohms. And I get 5.73 volts. These two should add to 18, which they're going to look like 18.01. Questions so far? Doing good? Now, how about the current out of the battery? Well, what we just said over there with our Kirchhoff's laws is that current flows in, it has to be equal to the two currents that flow out. So I can take 8.18 plus 10.23. Now I can do power. 18.41 times 18 is 331.4 milliwatts. 18 times 8.18 is 147.2 milliwatts. 12.28 times 10.23, 150. Wow. Skip the number. 125.6. 5.73 volts times 10.23. 58.6 milliwatts. Check really quickly. 58.6 plus 125.6 plus 147.2 is 331.4 milliwatts. As long as I have a resistor circuit, it doesn't matter if it's series, parallel, total power dissipated has to equal the total power in. Just a good check when I get all done to go, hey, is all my power in equal all my power out? Especially these series parallels, which aren't so straightforward. I just add voltage in the columns. Having said that, you guys should be able to handle, hey, this is parallel with the battery, so 18 volts. This is parallel with the battery, so it's 18 volts across those two. These two are 18. current comes out, splits, goes through these two. One of them, and that is the other one. Okay. Think you can handle these? Sure. These are basically the lab this week. I just want to talk real quick about some other ones we can think of. Your textbook has a detailed example. I'll let you read it. I can work through it when we meet next time if you'd like. But let's talk through it real quick. So, yeah, read this in the text. They have a battery. I think you end up solving for all the voltages and currents in that, just like we have. You certainly can. So if I want to solve those, how do I do it? Well, I have to take these two and combine them to form a single equivalent resistor. R1 and R2 are in parallel with each other. R3 and R4 are in parallel with each other. So I end up with the battery voltage, R12, R34, those are in series. So I would go find my current, right? I have a series circuit here. I can find the current through this, and finding the voltage across both of those. Okay, Ohm's law. Then I come back here. This voltage, this resistor is the equivalent of these two, so this voltage applies across both of them. Same thing for the next. And at that point, I can use those voltages, the resistors, to find this current, this current. So read that one close, because you're going to have 4 different currents you're going to end up with. Actually 5 if you count the battery. So think about this. These two currents, I1 plus I2, have to equal I3 plus I4. Neither of these will be equal to either of these, but when you have a current that flows out of the battery, splits, goes through these, comes back together, splits, comes back together. You have some other problems in the homework that look like this. These are just to make sure you can handle them. Oh no, 5 resistors. But these two are in series, combine them and get a single resistor. These two are in series, combine them and get a single resistor. So then you'll have an equivalent circuit with 3 resistors. It's exactly like our first example. And you work it. So it's always reducing your total number of resistors by finding series and parallel combinations to simplify the point you can work the circuit. And then take those voltages and currents you find in that simplified version and just work back. What I do is I just lay my schematics down the page, and then I just start working back up the page, doing Ohm's law to find all my voltages and currents. So I think what I'm going to do is turn you loose to work today. So work on homework. If you have lingering issues from last week, I'll take some time to work through those here in a minute, because I want to make sure you need series and parallel down before we're ready to do series parallel. But this week's lab, like I said, I think it's 3 circuits. If I lied, it's 4. Let's do it. But when you do those, make sure you work them first and then build them. Work them, build them. Make sure your measurements line up with what you work. And if they do not, talk to me. We'll figure it out on your own if you can, and then talk to me. And And feel free to talk to each other and go, hey, I keep measuring this, but I'm getting this. It could be that you're building it wrong. It could be that you solved it wrong initially. Hopefully it's not both.
Have fun.